Alright, so we're doing the more optimized backwards pass. I decided I'm just gonna go through it. I just copy and pasted it here. I'm just gonna go through it line by line, along with the visuals that we have. We can get rid of this one. So we'll use this visual to help us with it. First off, will admit I did use Gemini to help out with this. Sometimes Gemini is a genius. You just have to know, you just have to understand well enough when it is and when it is dumb. And hopefully I'm helping you out with that a little bit. Just understand concepts, the concepts you're needing, and let it generate the ideas, and you figure out, is that a legit idea? But yeah, so first off, getting the derivatives of the A weights and B weights. Start by filling them with 0, because we are going to, as it says here, we're going to accumulate them. And then we're going to, this time we'll actually use these. We'll make some variables here, N, I, J, R, batch size, input features, output features. There we go. I like that. And the rank. Once again, you just copy the layer bias from the dense layer. You could just put this in a different function or something. So you don't have to copy it both times, but it's probably too late by now. Okay, so here's where we calculate everything for the weights and the inputs. First, we're going to go through each sample. So this is number of samples. So each little n is a sample. Then we are going to iterate through the rank of each of the the rank of your B and A matrices. First thing we're going to do here is create this, you can call it whatever you want, gradient, projection, scalar. I should have changed that name, but whatever. So what this is going to do is combine, remember how we were combining D values with WB to get that dval WB matrix. So this is going to do that in pieces. If you think about a matrix multiplication, you are multiplying two things together and summing them up into one value. So this is going to act like it's one piece of that matrix, and we're going to, that matrix is going to go through these two. So this, to get a visual, NJ and RJ. So to get a visual of that, so that's multiplying these two pieces together. With this one would be transposed, so let's do that. Oh, not what I wanted. Let's see, 1, 2, 3, 4. 1, 2, 3, 4. Perfect. All right, so this is a 3x4, and this is a 4x2. So what this one right here does. We're going through one sample, which is, let's see, one sample, and then 0th sample, 0th rank. So that's the first part. 0th sample. So this is the samples 0, 1, 2, 3. So we're 0th sample, which is right here. 0th rank, which is right here. We're going to combine these. We're going to do this first x times first. So first one times first one plus second one times second one. So basically doing this portion, well, that doesn't work. This portion of the dot product right there to get the first part of dval wb. And that gets put right here. Goes to j. J was, let's see if I can put this down. So J is dvalues.columns. Dvalues.columns is across these columns, which is equivalent to down these rows, because they're multiplying together, or dotting together, maybe I should say. So you would have where I'm at. So gradient projection to get that first number of the dval wv, you'll do dvalues first or 0th row of the dvalues matrix, and you will iterate through the j's, which is the dvalues columns. You will go through the wv's, staying in the 0th rank, going down the j's. So you get the gradient projection. You're going to do a similar thing here with this input projection scalar. So that will be in I and IR, which is, let's visualize that. Where's it? Right here. So that will be going across this N for 0th sample, going across N, and going down 0th rank, so going down. So it's the same. Multiplying that row with this column, getting the input, what we called imp WA, input with WA. So, but it only gets one piece of it, one value of it. And we're going to do that, we're going to do that over and over each of these, so that you get a matrix of them, basically. But you never create a matrix that you put into storage. We're just going to calculate, use it, and then calculate again. Calculate, use it, throw it away. So we got, that, and then that. And next, get rid of this. We'll apply those midway steps by doing a dWb is equal to that projection scale. So we're going to start with the projection scalar times the d values. And like I said before, I think it was on the last video, go ahead and print out anything you need to kind of visualize things to make sure it's more concrete. But get the dWb. We are going to combine d values with imp WA. And this input projection scalar is a piece of layer inputs with WA. So that's the imp WA, but just a piece of it. And we're going to iteratively multiply that with the D values to get the DWB. And then we're going to do the same down here for the weights. Let's see. So it'll get another for loop to do both the DWA and the D inputs. We can do both here at the same time, so might as well. The gradient projection scalar, which yeah, I definitely should rename. I'd probably rename that to like dval WB scalar, and this one could be imp WA scalar. Yeah, whatever. So you take that, multiply with the layer inputs. So this one is, so DWA, so this is dval WB scalar with layer inputs, and multiply that and add to get the DWA portions. The gradient projection scalar, the same thing, dval WB times WA will get you the D inputs. Let me go through the visual. Dval WB, which is, okay, so dval WB is that this part combined with this part. Remember, it's only pieces though, so this part combined with this part gets the one portion of dval one number of dval WT or WB. Those go together and multiply with a part of the input, because we're right here getting DWA. These two pieces, aka these two pieces, go together with the input to get the derivatives of this. And then you're going to do the same kind of thing with the D inputs. In order to get the derivative of this, you're going to take that dval WB, which is a combination of these two, multiply it with A, and that gets you the derivative of these. And that's it. You got DWA, D inputs, and DWB. This will for sure, like, understanding this is going to get much better. Eventually I'm going to go into using the GPU for all this coding. We're going to learn, well, I'd have you use Elliot Arledge. I think I said his name right. His CUDA course. Let's see.
Row in A.
Use that to do a lot of, it's a 12-hour course. Use this to learn most of your CUDA stuff. As you can see, I'm not even fully through it. But I've looked at some other resources for some of the different CUDA, learning CUDA, like softmax and other different stuff. But yeah, I'd have you watch this video before you get into any of my CUDA stuff. I would say he's probably better at explaining. Maybe I can complement some of the pieces. But yeah, so there's that. Oh, there we go. So yeah, once we get into using a GPU, this will be way better to understand, because the really slow thing on GPU, even on CPU, but especially on GPU, would be accessing memory, all these different memory pieces. The best thing to do would just be what we do right here. Boom, one double. You will have to access these. There'll be tricks for faster access on this, like using shared memory. But access as few things as possible. And boom. But yeah, that is Lora. Well, I guess we should probably put it into the image and then, which is really easy. All we do is replace this with a Lora. The arguments are going to be wrong. Let me go back. First, let me save this. What are the arguments? So inputs, outputs, bias, num samples. Oh yeah, need one piece. The rank. Let's see. Let's actually. I'll let you go ahead and do it right here if you want. Otherwise, you can just copy it into. I'm gonna copy it into another project. Let's see. Yeah, we'll just throw it out here. We will call this Lora image, and I'm just gonna copy what just happened? Weird. Okay, so I'm just gonna copy all that. Go to Lora image, paste all that. We're gonna add, okay, so we got rank equals 4 already in here, sweet. We're gonna replace this with a Lora, and we are gonna add in rank. Boom. And then that should be it. Should be able to pull this up. 300 iterations. Now it will not be as good as a full rank matrix. Layer dense. Let's see. Of the one. Oh yeah. I guess one more thing is needed here. We need to go back to nn.cpp and go down to the optimizer and add in another update params. So actually I've known how to do this for a while and didn't know what the name was. So this is polymorphism right here. Just recently learned the name. Yes, I have an interesting learning path. But let's see. Let me go down to that. Where is it at? Okay, so this is actually really simple. Okay, so we put this in here, Lora layer, the void update params, Lora. And then we're gonna throw this right here. update params, Lora layer, and it's just as simple as the update up here, except instead of just having, so you'll have, once again, you can just copy, that bugs me, copy layer bias. It is not changed at all. But this time, instead of going through just the layer.weights, we're going to have a layer.wa, weights A, and we're going to have a layer.wb. And you just loop through each of those, updating the weights with the derivative of the weights. Simple. For I, WA, just kidding, layer.wa.rows, layer.wb, wa.calls, and then I'm just going to copy it because it's a lot and I'm getting tired. The layer WA matrix minus learning rate times derivative of WA. And then do the same thing for WB. Loop through WB, rows calls, update WB with derivatives of WB. Save that, and come back over here to Lora image. All right, that should be fixed. Lora, no suitable user-defined conversion from Lora to layer dense. Did I save this? Control save. Control save. Dense layer. Image gathering.cpp. nn.cpp. Lora. Lora LD1. All right, what am I missing here? Okay, where is image gathering? Image gathering's right here. Which references and then okay, we're gonna just change it to 01. So Lora. Conversion from Lora to layer dense exists. Okay, so we're gonna update params. I don't know why that's not working. CPV. Weird. Okay, so I think the problem is because I have two NN files. Let's rename this NN. Interesting. Okay, give me 1 second here. Oh, okay. So this is why. I do want that down there. It's because I just reclassified this class. I've basically done it twice. Okay, so we're gonna copy this. And put it down here at the bottom. So it should be fine for you, for anybody watching. For some reason I had two optimizers. I created this optimizer class twice. But yeah, that's why it was not working. Date params. I knew it was supposed to work. Okay, so there's that. Did I get rid of the other optimizer? Not yet. Optimizer. Oh, okay, I called it optimizer. Optimizer. Is that what I used in all of this? Let's see. SGD. Yeah, okay. Yeah. Now we're gonna have an issue probably because I didn't copy that correctly. Optimizer SGD, update params. This one still says just optimizer. So for you, either way, if you had optimizer SGD or just optimizer, use the corresponding class. I assume you don't have both. I don't know how I put both in there, but yeah. Control save. All right, there is no issue down here. So control save and okay, it works one time. Bring it back to 301 iterations. And let's see what happens. Eventually. 217. It's a little sporadic, but it does update. It does get better. It's not as good as the normal training. We also do have a really low rank here. But as you increase the rank, you increase the time it'll take to train. I just tried it again. See if it trains better with 500 iterations. Of course, that'll take a little longer. But yeah, it gets sporadically gets there. If we were to use like, I mean, because we are going from a 28 by 28, so what's that, 700 and something by 256 matrix down to a 700 by 2 and 2 by, or what was it, 4, 700 by 4 and 4 by 256. That is a huge difference. Let's make this 8. Go back to 300. So that doubled the size. That'll definitely make it slower. But you can play with these numbers, see what you get for yourself. Okay, so this new one went from 5.1 down to, it gets better. But yeah, it's not near as good because it is way smaller. But yeah, that's it.